All right. So, um, today's a little bit of an extra lecture, but it's really just making up for at least one of the lectures we missed. So, basically today I'm going to talk about binary search trees. So that's kind of fun. Hopefully people catch up on this lecture if they don't watch it live. So, yeah. All right. So, let's forget about Big O and the stuff we did last time for just a little bit, and let's just think about a data structure we make like this, right? So what we're going to do is we're going to have nodes, and those nodes are going to be like little circles. Maybe I'll make it smaller. Okay, so let's decompose this term binary. Binary just means 2. So what that means is that these trees will each have 2 children. I shouldn't say 2. I should say at most 2 children. So each node will have these nodes in the trees. Will each have. That's probably the best way to say it. So, okay. And then what does the search part mean? The search part means, and I'll explain this in just a second, basically if it's less, you go left. If it's bigger, you go right. And that's really it. That's what the search, at least for a binary search tree, that's what it means. And so, okay. So basically it's kind of like a linked list, except in this case what we're going to have is that each node can have up to 2 children like this. So instead of having a like next pointer, you're actually going to have 2 different pointers. You're going to have one that is quote-unquote left and one that's quote-unquote right. So basically if this is your node, if this is the current node, then this is current dot left, and maybe I need to make the font smaller or make the whatever bigger. Well, whatever. And the other one is going to be current dot right. And so that's really it. And so each node is going to have some data in it. So for instance, like maybe this node has say the number 5 in it, and this node has the number, say, 3 in it, and this node will have the number 12. And so the question is, how do we know if I'm searching for 3 in this binary search tree, how do I know which direction to go? And the answer is well, if you're searching for something less than the current node, you go right, else left. Now, you can. So what I mean by else left is technically you could also have a node that's equal. We don't really have to discuss. So the thing is, there's nothing that in a binary search tree definition that decides this. You can say if it's less than or equal to, then go left, or if it's greater than, then go right. But the point is that the equal sign isn't going to really affect anything other than the specific implementation. And so you might say, okay, well, this is a fine binary search tree, but can I make the binary search tree bigger, right? And so the answer is, yes, you can. What you can do is basically copy-paste this, stick it on here, and then we change these values. So basically, how should I explain this? So what I should say is that anything that goes in here, right? So anything that goes in this spot has to be what? So there's 2 rules for it. It has to be less than 5, and it has to be bigger than or equal to 3, right? So that's the rule for this. And the reason why that's the rule for this is because it came from something. Here's what we call here the root node. And so then the root node has what we would call children. And so the root node has a right child and a left child. And the left child is always less, the right child is always greater than or equal to. And so here, basically, if I'm trying to insert a new node, say I'm trying to insert the number 4. If you are inserting 4, for instance, and let's say that this is our binary search tree currently, this node doesn't currently exist, then what you do is you take the number 4 and you ask the question. You say, are you bigger than or less than 5? The answer is you're less, so you're going to go this way. And then you say, are you bigger than or less than 3? And you say bigger, so you go this way. And what you notice here is that at this point you would say, oh, this node doesn't have a right child. The child would be like a null pointer, right? So because it's a null pointer, what we get to do is insert it there. So that's basically how we get to do this stuff. So for instance, let's try it again, only let's insert 8, right? Let's insert 8 into the structure. And so how do we insert 8 into the structure? We do the same thing. We say 8. Are you bigger than or less than 5? The answer is you're bigger than 5, so you'll go this way. And finally, you'll say 8. Are you bigger than or less than 12? Well, you're less than 12, so you're going to go this way. So unfortunately, as it turns out, binary search trees can grow exponentially, because you see that if you have one node at level 1, you have 2 nodes at level 2, you have 4 nodes at level 3, you have 8 nodes at level 4, etc., you're going to run out of space pretty often. So, and I don't mean actual memory space, what I mean is literal, like if you're drawing it, graphical, physical space. So I'm going to shift this node over. This is still the right child, even though I'm kind of drawing it almost directly under. The only reason is because I need to make space for this left child and maybe a null pointer over here. So when you're doing your drawings, you might find that you need to like think about, I would say generally what you do in your drawings is you always think about, who or how far down do I have to go first, and that decides like how big your tree should actually, how wide your tree should be, and you should always put in some extra width. I'm just kind of, using this. Okay, so basically this is a binary search tree, and it's a binary search tree with, I guess, 6 nodes in it. And so the whole point of this binary search tree here is that whenever you insert something, you're just going to ask the question. The question is it bigger than or less than whatever? So for instance, let's do one last one. Let's say that we were going to insert -5, right? Because I just want a number that's less than 1, so -5 is less than 1. So -5 is less than 5, -5 is less than 3, -5 is less than 1, so it becomes the child here. Okay? Something like this. There we go. And so you might say to yourself, well, this is not a balanced tree. This looks imbalanced. And to that I say, yes, it is. Nothing in the rules, right, requires a BST, or binary search tree, to be balanced. Basically the whole point of learning about binary search trees is that next week probably we'll start doing splay trees and AVL trees. So there are 3 types of balanced trees that we talk about. Basically we talk about splay trees, which are quasi-balanced. They're sort of expected value balanced. And then there's AVL trees, which are very strictly balanced. And then there's red-black trees, which are slightly lazier in their balancing, but generally they require fewer operations, which is good. So they're kind of a balance, a balance between AVL and well, I guess they're not really a balance. They're just a different way of thinking about balancing trees. They're not really. It's not really a contest or anything. It's AVL and red-black guarantee balance. Splay trees do something slightly differently, but either way, they are, all 3 of them kind of do some kind of balancing operations on a tree. So, I think that's good enough for theory right now. I think we've discussed at least the basic theory of a binary search tree, right? It's either you go left or you go right. So all I really want to do now is implement one. So let's use the Big O project that I made. And let's make a binary search tree class. What should we call it? Let's call it BST, maybe? Okay. So what kind of things do you do in a BST? Right? You'll need a constructor. We might even want like a copy constructor. Maybe we'll have an assignment operator. And then the interesting operations. So this is all just kind of, you know, C++y stuff that you need. So what's the kind of interesting things that you want, right? We want like an insert, and for now we're just going to do integers because integers are cool. So we'll insert integers. There's also, we'll have a remove method, which I haven't told you how to remove yet, but and then maybe a find. So we'll discuss voice, and of course anyway. So find int data. So this might be either later today or next week that we talk about removing things from binary search trees. So it's a different operation, but right now we can do insert, find. Maybe we'll talk about the destructor. Yeah, we need a destructor. And what else do we need? I guess that's really it. So just like a linked list, right? So a linked list has a a linked list has a head. So the reason, I think one of the main reasons why they call linked list things heads is because of like old-fashioned, you know, magnetic tape readers and heads, basically. So anyway, I think that also it's at the top. So I guess that also it's the top. Well, so you can call it the head here too, but generally we call the thing that is at the base or the head of our binary search tree, we call it the root. So I'm going to call it proot because I like to make it a pointer. I think according to core standards you should make it like mroot. I'll leave it. Okay, we'll follow core standards. We'll make it mroot. So okay, cool. So now we want to make a tree node pointer, and you say, you know, but Eric, you didn't do that yet. You didn't make a struct for the tree node. Okay, I'll do that. Here we go. So yeah, so oh, and there's one last thing that we should do. We should make a display method. And I think I have an idea. So we'll have a private helper method with tree node pointer p current. Okay. And so this is all you really need in a binary search tree. Just like a linked list, the basic linked list, you know, technically if you have, you know, like a pointer to the end or some other kind of pointers, something that, you know, if you save the length or if you save other things, you can have other private data members. But this is like fundamentally all you actually need in a, you know, in a binary search tree is the root. Okay, so we'll have display, and then here we have this. I'm just gonna, display is not something that you have to necessarily, oh, and then I like to do it this way. So I think it helps if we do it this way, int depth. Whoops, wait, what the, oh, sorry. There was something on my mouse causing, or something on my arrow key causing problems. So let's see, depth equals. Okay. I guess we'll put this, here. Okay, cool. So now that we've gotten all that done, and of course I'm spending way too much time on display subtree, whereas I should actually be spending the time on implementing insert and find, which are the more interesting operations. So, okay, let's just copy paste all this stuff. Oh wait, no, I'm sorry. What haven't we done? We haven't done this. So tree node, let's make a little constructor. This little constructor will save us some, This little constructor will save us some annoyance. So let's make a tree node, let's see, tree node pointer p left, and then pointer p right. I always have to remember that if you're going to do something like this, you always have to remember that if you're going to make 2 pointers, you need to have the pointer on both of them. I always forget that because I always think like, oh, I'll just make a tree node pointer, and then I always comma, and then I'll just use a regular variable name, and that's never good. So data. So that's really all we need in there, I think, right? I think that's all we need. So yeah, a ternary tree would just have like left, right, and like a p center, right? But generally, we don't actually teach the ternary trees in this class. I just used it as a mathematical, amusement, a bit of homework goodness, right? So let's say new data that way, and then what we can do is we can actually just set data. There we go. Okay, so I think this is all we really need. Technically, we don't even need the space in here. We can just kind of bracket it like that. Okay, and the only reason why I'm doing this inside of my tree node is because if you don't set these to null inside the constructor, then they're going to be random, right? They're going to be calling from just garbage memory. And so what you're going to end up having is, if you don't set p left and p right null pointer, then you're going to end up with some trouble, right? And that's really the key here. So you're just going to end up with some trouble. You'll end up with weird Valgrind errors, some stuff that you can't identify. It's going to be really hard to figure out what's going on because, because that's how it is. So, okay, so that's why I do it. All right, so let's go to the bst.cpp and let's copy paste all these functions. And I mean, so the thing is that the data can be strings, the data can be anything. The only requirement that the data has to satisfy, so I always make it integers, at least for our first examples, but the only actual requirement that it has to satisfy is that the data just has to be what's called comparable. So it just means, so comparable data in this case just means that like less than equals and greater than, and obviously like greater than or equal to is less than or equal to, not equal to, need to work, right? If they don't work, then it's impossible to tell if 2 things are, in various orders. And you notice that the binary search tree, the one thing it does is it preserves the order. It puts the order of elements into the tree in certain ways. So, so that's what we need. Okay, and so let's do that, and then here we can delete the private, and we can just do this. Okay, cool. And now we can finish our implementation. So the first thing we should do in our implementation is when you're creating a default structure, we'll just create mroot and set it to null pointer for the exact same reason. We don't want it to be causing trouble. I'm going to leave the other 2, the copy constructor here, and I'm going to leave the assignment operator undone for now. And I'm going to leave the destructor undone for now. And we'll come back to those later. Let's do insert and find first. I think, insert and find are almost the same. Because basically, well, yeah, let's do find first since it's a slightly easier version of insert. And so basically what we do is we say if mroot, right? So if the root is not equal to null pointer, or actually what we could do is even better. We could say tree node pointer p current equals mroot. And then what we do is we say while p current is not equal to null pointer, right? And so now what are we going to do, right? So now what we're going to do is if our data is less than the current node's data, we go down and to the left. Let's see, am I right? If the data we're looking for is less than the current node's data, yes, we go down and to the left. If the data is greater than, right, current node's data, then we go down and to the right. Okay. So let's see what happens here. Oh, this should not be a void. This should be probably bool, right? Like, did we find the thing or not? Oops. Let's fix that in the .h file. There we go. Done. Okay. So, what are we going to do here? So the answer is basically what we're going to do is we're going to say if pcurrent dot data is, say, let's just do it the way that I've written it. So if data, right, the data we're looking for is less than the pcurrent's data, then we say, okay, pcurrent is equal to pcurrent dot pleft, and that's all we got to do for now. Else if data is bigger than pcurrent dot data, right? And then we go, okay, it's bigger, so we go pcurrent equals pcurrent dot prawrite. And the last thing we have to do, so this is something I didn't really talk about because I don't know why. So yeah, so what if none of those are true, right? What if it's not less than and it's not greater than? There's only one option left. It's the property of trichotomy, meaning that it has to be less than, greater than, or equal to, right? So if it's equal, we just return true, right? So if we find the piece of data, then we can just return true. Here's what we do to keep searching, right? So this is exactly what we do if we have to keep searching. And you notice here that it's kind of like a recursive process, but it's not really. So there's a way, so maybe I'll just do it this way, and let's finish this function first before I jump ahead as usual. So what if the thing finds a null pointer? So let's look at our little example here and say that we're going to search for the number 7, right? So we're not inserting 7, we're searching for 7. So if we search for 7, what we're going to do is we're going to go 7 is bigger than 5, so we go right. It's less than 12, so we go left. It's less than 8, so we go left. And then what happens? What happens is we fall out of the data structure, also known as, right, AKA, we've hit a null pointer, right? So in C++ language, you would say, I know what's going to happen here. We're going to hit a null pointer. So when we hit that null pointer, we know that the thing was not in the data structure, because the point is what we did was we said it's bigger than 5, less than 12, less than 8, but there's nothing like that in this data structure, right? So if we were searching for 4, for instance, and we said 4 is less than 5, it's bigger than 3, and it's right here, right? So that's when we return true. If I search for like -5, I say -5 is less than this, less than this, less than this, and here it is. But if I'm searching for 0, I say 0 is less than this, less than this, less than this, so I go this way, bigger than this, so I go right, but then I fall out of the data structure again. So the point here is that, if you search through the structure using the rules, then if you find a null pointer, then that object you are searching for is not in the BST, right? So that's the point here, is that the object isn't actually in the binary search tree. So what can we do? So what we do is return false, right? if we get to the end of this function and we haven't returned true, we return false. Not false, false, like that. And so you see here why we do that. We do that because we're going to search through the data structure. If it's less, we go left. If it's less, we go left. If it's greater, we go right. And if it's equal, we just return true. And then the only last thing we have to do is that if we've searched through the data structure on our way down, then we'll return false. And so this actually brings up what the kind of point. So you might be asking at this point, what's the point, right? Why do we make these things? And so the answer is because all searches through this structure become binary searches. And we basically avoid searching most of the elements in a tree in order to find a specific element, right? Because if you have an array, right? If you have an array and you want to search through it, you know, if you just have an array or a linked list, unsorted, then basically what's going to end up happening is you need at least O of n time, and of course I lied about forgetting about O of n. We need at least O of n time, well, exactly O of n time, to search through this list, array, linked list, right? So that's a problem, because what if n is large, right? What if n is large? The point is that it's going to take a long time to do a search operation. And let me promise you that in the vast majority of data structures, searching is like the most common thing you're going to do, right? You're going to either insert, find, delete. Those are really the things you do in a data structure. And so if you're inserting into a data structure, you're also doing a kind of find operation. But if you're doing just search operations, you want them to be as fast as possible. So when we talk about hash tables, we'll see how to basically make something into an O of 1 operation, an array into an O of 1 operation. But this is kind of like a predecessor type of data structure. This makes searching, at least in good cases, on the average case of binary search trees, it makes the search take O of log n time. And you see that log n is going to be way, 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 way better than n. And so why is that way better? Because if you think about it, if we're just talking, say, log base 10 and being lazy here, then, you know, if you have an array that's, say, 1 million in length, then that's 1 million steps in O of n, right? Or some constant times a million steps. So it could be 5 million steps, or it could be 500,000 steps or something like that, but it's going to be about 1 million steps. Whereas if you have a million size array and you're doing a binary search tree, that means you take the log of 1 million, and that means 6. So you can find a huge number. So you see that doing 1 million steps versus doing 6 steps, and there is no comparison. And of course, LG is log base 2, so it's not exactly that. It's some constant multiple of that, so it's more like, say, 12 steps or something like that. But like, the point is, who cares, right? You're not doing 1 million steps. You're doing 6, 8, 10, 12 steps for 1 million elements. And if you, say, had 1 billion, right, elements, the BST would do the log of 1 billion, which would be something like some constant times 9 steps. So increasing the size of the data structure only increases the expected amount of search time by, like, if you increase the size of the data structure by 10, you only increase the expected number of steps by 1. Whereas if you have an unsorted list, then if you increase the size of the data structure by 10, you increase the search time by 10. It's just a straight thing. Now you might say, what if we sort the array? But then actually the secret is that you use binary search, which is almost the same as a BST, if you think about it. And I might go over that later, but so that's what the point of this thing is. The point of this thing is to be able to recall data real fast. in as few steps as possible. Now, it's not one step, right? That would be beautiful if it were just one step, and it's not one step, but it isn't equal to the number of things. Now, it's always possible to make a very bad and unbalanced binary search tree, so that's why I say average case here, or expected case, or you might say best case is also applicable here. All of that is true. So there are worst cases in the binary search tree, and we'll discuss those later. But for now, this is how to do find. Okay, so let's do insert. Okay, so insert is a lot like find. Right, what we're gonna do, oh my, playback error occurred. How's that possible? Am I still online? Okay, looks good. Okay, so it's a lot like find, except at the end, we stick in the data, right? And so that's basically how we distinguish here. So we can almost just copy-paste our code here. So let's do that. Let's copy-paste our code from find, because we are good programmers. And so here, what I'm going to do is I'm going to say if the data is bigger than or equal to, go right. And if it's less than, go left. So that's the modification that I make. I take out the equal part because we're not trying to find the data. And if we insert multiple copies of the same data, that's okay. Binary search trees can handle having multiple values of the same, multiple things of the same value in the tree. Okay, so we got to modify this just a little bit. So basically the point is here, instead of saying this, right, we check if the thing is null pointer. Well, if it's null pointer, I want to insert. But I can't insert at a null pointer, so we have to kind of keep track of the parent. So here's one way to do it. I mean, this is not always the, whatever. Parent equals null pointer. Okay. So here we actually need a little bit of an edge case, which says that if mroot, and so notice that I just say not mroot. Basically, this is the same thing as saying mroot is equal to null pointer. C++ definitely evaluates the not operator correctly in this case, so you should feel free to use it. So if the root doesn't exist, we need to add the root. There we go. Cool. And so, and then I guess actually we can just return, right? So we don't have to do anything else. Technically what we could do is just add an else here, but I like, so I'm trying different coding styles out, and one coding style has, just says, instead of doing an else and tabbing everything in by one, just do a return here, and then you don't have to tab everything in, you don't need the else block, etc. I'm actually not sure which one is better if you like compiled it down to assembly language. I honestly don't think it matters all that much. It might even get compiled down to the same assembly language code in the first place, so it might not even matter. So basically here, so parent is going to be set to pcurrent. Here, parent is going to be set to pcurrent, and then we'll keep going until pcurrent is null pointer. And then what we're going to do here at the end is we're going to say if the parent, which is guaranteed to not be null pointer, right? Because if it's null pointer, then the mroot was null pointer, or the parent of the null pointer was also null pointer, which is, so the parent is not going to be null pointer. So if parent.data, or if data is going to be, I always have to do it this way. I have to be very specific. I know that it doesn't matter if if parent.data is bigger than data or whatever, but it confuses the crap out of me, and I end up making mistakes. So reference may be null. So let's see here. So actually, this will never be null, even though it thinks it might be, but it's definitely not going to be. Okay, unless I've made a mistake. So, okay, if the data is less than the parent.data, then what you do is you insert it at the parent's p left is equal to new tree node data. Else, you do the same thing, but on the parent's right, like this. So this is actually a different implementation than I've ever, a different specific implementation that I've ever done before. Just trying something new out, so it might fail horribly. But I kind of like it. It really does use the find operation. I think it's good. I think it's good. So yeah, so we're doing something a little tricky. So the CLion can't understand why parent can't be null. So even though parent is set to null up here, it can't be null because as soon as we run through this loop once, if pcurrent was equal to null, pcurrent was also equal to mroot, so then mroot would be null. And so if pcurrent isn't null, then we set the parent equal to the mroot immediately, and by the time we get here, it will never have been set to null. So this is actually, it's good that it's telling us this, but it's not possible. Or if it's possible, then I've screwed up. Okay, so actually I think I like this implementation a little bit because it's actually a little bit more compact than the things I've done in the past. So you know what, I'm on board with it. I'm kind of liking it. Anyway, let's so we've done insert, and so now what we're gonna do is display, right? And so display, you might think, well, how do I display a binary search tree? The answer is what you do is you call the helper method. And you're like, okay, that's stupid. All right, so okay, now you're saying, okay, don't mess with me anymore. I want to know how you display a subtree. So what I'm going to do is I'm going to, I think this is a good way to see it. I can't really draw it horizontally down or up. That's a little harder. So I'm going to draw it like laterally, and you'll see what I mean by that, or like, what should I say, horizontally. But okay, so what I'm going to do here is I'm going to say for int I equals 0, I less than depth, I plus plus, and I'm going to see out that number of tabs. And no end line, just that. And then what I'm going to do here is I'm going to say, okay, now I'm going to output. Well, I guess we could do all kinds of different tree traversals. Let's do the display subtree pcurrent dot p left. So if pcurrent dot p left, we'll do this. So actually we need to check if pcurrent as well. So if pcurrent, right, because if pcurrent is null pointer, then we have a problem. So else we'll see out, I guess we'll do the tabby thing, and then we'll see out, well actually if it's null pointer we shouldn't display anything, unless actually, yeah, maybe I'll add this, and then I'll say, you know, if and you're like, what the heck is that? So this is something that you're not going to have to really worry about too much. I'm just kind of making this up as I go along. Okay. And I want there to be a Boolean verbose leaves. And here what we can do is we can say bool verbose leaves equals false. Okay. So the only reason why we need the display method, like technically this is just something I'm making up right now. This is not 100% part of like a binary search tree data structure. The reason why I'm doing this is just because if I don't, we can't see anything, and so we can't know if we've done anything right or wrong. So that's a slight issue. Okay. And so then what we're going to do here is we'll see out the pcurrent data, and then we'll end that line. And then we'll do, so actually we don't need this. We can just do this. And then we can say display the tree on the right. And so let's see what this does. Hopefully not segmentation fault. Most likely it's going to be segmentation fault. Because that is the kind of coder I am. I am the kind of person who will cause a seg fault in like 5 seconds. Okay, so, alright. So, we got that. And then we just need here, we should add that to here, and then add that to here. Okay, so generally we're not going to output it, but maybe we will. Of course I didn't put a Boolean type because I've done so much Python that I've forgotten how to code. Okay, so here's the display method. You don't have to worry too much about it. It's actually doing an in-order traversal, but again, you don't have to worry too much about it. It should display everything that we want in a kind of decent way. So let's write some driver code that actually tests these things out, right? Because we haven't tested anything out yet. So we don't have these operators yet, and we don't have the destructor yet. So maybe what I'll do for the destructor is I'll just delete mroot, and then I'll add a destructor into this. So this is generally not how they do it in this class. The reason why they don't do it this way is I don't know why. But anyway, yeah, so if you delete a tree node, then what we're going to do, let's say yep. Okay, so what we'll do is we'll just delete p left and delete p right, and that should clean up our structure. I'll explain how that works in just a bit, but until then, let's just delete all these test sorts. Right, so all this code doesn't have any errors in it, so the good news is we can just include the BST class, and we shouldn't have any problems if we just make our driver code here. So let's say void BST driver, and let's make it, let's call BST driver, call it. Okay, so let's say so while s is not equal to say quit, we are going to do the following things. So if, say, s is equal to, say, insert, then we'll insert. Else if s is equal to find, then we will find. Else if s is equal to display, then we will call the display function. So let's make a BST class, BST, and so we'll do CNX BST.insert x. Okay, and then let's make an int x. There we go. Okay. So then we'll say CNX if BST.find x. We'll see out we found x and y. Else we did not find x. Okay, I think all of this is getting there, right? We're pretty close to having driver code that runs. And then here we'll just do bst.display, and And then here we'll say else if s is equal to display with leaves, we'll say set this to true. All right. Why is there an error? Semicolon. Why is there an error? Semicolon. Cool. So I think we're good. I think we can run it, and we can see what we can do here. Let's see what happens. How many times we have to segfault before something works. Oh, wonderful. Oh. We can't just, so, okay. All right, so that was stupid. Let's try it again. Okay, maybe we should have maybe we should have a prompt, because it just says, it just leaves us to input things. Yeah, so I think, oh crap, and also this is an infinite loop because I'm an idiot. So let's see out enter command, right? And then we'll see in. So before we get into that infinite loop business, and before we do anything terribly stupid, let's just, okay, there we go. Enter command. Let's display. Okay, wonderful. The good news is it did something because it output the space, but it didn't explode. Let's insert 5 and display. Okay, let's insert 10, right? And now let's display again. So what do we see here? So let me insert 2 just to show you how this tree is working. Oh God. Well, that's pretty horrible. Why did it do that? So it converted that tab to 4 spaces, and it converted this tab to a bunch of spaces. It's very strange. Did I do something wrong in this method here? Good question. Or is it just kind of messed up? That's too bad. I don't like this. Why did it screw up like this? This is weird. Weird. I don't know. Okay, well anyway, so the point is that the tree is kind of flipped on its side. This is the left subtree, so this is like the less tree, and this is the greater tree, so it's on the right. So technically, if you flip this tree vertically, you should flip it 90 degrees upwards so that the 5 is at the bottom and the 2 is on the left and the 10 is on the right. So for instance, if we then insert, say, 12, let's see what that does, and then display. Oh, okay, it's doing a little bit better. I don't know why it's not helping us out here. So let's insert 8 just to see what happens if it's causing the same problem and then display. Okay, so it's just this weirdness here. I don't know why this did that. It's so weird. It's like a different size tab to the rest of them. You know, we can actually fix that, I think. There we go. We can fix it. Now a tab is 4 spaces, or 5 spaces. Okay, so we're just gonna be, I mean, I don't know that that's a good thing or a bad thing, but instead of using tabs, we're just literally gonna use 5 spaces, so that the this thing doesn't try to auto-format our text for us and convert tabs to the wrong number of spaces and that kind of thing. I think the other modification I'm going to make is let's just have it display after every pass. That way we don't have to keep hitting display. So let's insert 5, then we insert 10, insert 2. See, at least now it's kind of balanced. Insert 15, right? So what this is doing is it's saying 15 is bigger than 5, it's bigger than 10, so it goes in as the less child of that. And so then if we insert, for instance, if we insert 8, then what's going to happen is it's going to go in as the right child. So left child is down and right child is up, right? So here, if we insert 8, we're going to see that 8 should appear right here. There we go. And this is not the child here, so these two are not connected. So for instance, if I insert 3, what you're going to see is that it'll space out, and then you'll have a child here. So now you see the levels kind of showing up kind of in a pretty way. Let's insert 100, insert 150, and then, so you see we can, so this is generating kind of the worst case for a binary search tree. So remember how I said that we expect that the number of steps to search for something is going to be the logarithm of the number of elements in the thing, but in this case you notice that except for these three weird kind of outliers, everything else here, this is basically just a linked list, right? We have a left pointer and we have a right pointer, but if we only ever use the right pointers, or we only ever use the left pointers, or technically if we use like right, left, right, left, right, left, always, then the point is that that's going to end up being a linked list, and that's going to end up with bad time behavior. So if we, let's actually try the find operation, because I haven't checked it. We found 8, good. Find 12, hopefully we did not find 12. Find 200,000, right? We did not find that. Okay, good. So as you see here, we can like insert other things. We can insert, say, 4, and then we can insert, and what happens if we insert a duplicate 5? What's going to happen is it's going to try to insert here, and since it's actually greater than or equal to this 5, what it's going to do is it's going to insert on the right and then all the way to the left. So it's going to look, it's going to show up somewhere around here, unless I screw something up. There it is. So it's the left child of the, it's the right child, left child, left child, right? So right, left, left, right? So, cool. All right, so I think that's good enough for a lot of this stuff. And I will try to make sure that I post this thing to the actual GitHub too. Okay, so let's quit. Hopefully quit works. Cool. So this is a binary search tree, right? And so we've done a lot of stuff with binary search trees. We've inserted, we've found, and so now, and technically we've constructed and destructed. We haven't done these things yet. We haven't made copies. If you want to make a copy of a BST, a lot of times it's helpful to have a method, right? Well, you could have like a copy subtree method, where you have a tree node pointer pcurrent, and then what you do is you would just, maybe we'll even say a tree node pointer is going to be returned here. So if we say if pcurrent, then else return null pointer. And so what we can do here is we can say, let's make a new tree node with the pcurrent data, like that. And then what we can do here is tree node pointer, pnew equals this. Then we say copy subtree on pcurrent.pleft, and we'll assign this to pnew.pleft equals pnew.prawrite is equal to copy subtree. And so I'm using recursion here because what I'm doing is I'm saying what we're going to do here is we're going to copy. So here's what we've done, right? At every node, you can make a copy of the data structure by copying the data into a new node, then you copy the left subtree, then you copy the right subtree, and then you return the current new node that you just made. So then what we can do is we can return the pnew. And so then the only thing we have to do here is we basically say, copy subtree of this .mroot, and we say mroot, our mroot, right? This is our mroot is equal to, is set equal to the other BST dot mroot but copied, right? So this will make a deep copy. Now, of course, you're going to say, but Eric, you didn't make this a member of the class. And I would say, you are technically correct. The best kind of correct. So I'll do that now. And generally, you'll make these like copy helper methods private, right? Tree node pointer. There we go. So that's fine. That's one way to do it. I'll show you other ways to copy. This is just one way. There's another way it's also recursive. So basically, every copy operation has to be recursive because here's the argument why this has to be recursive. It has to be recursive because unlike find or insert, right, where we only go down one path, to make a copy, you must go down all possible paths. And all possible paths means you have to go left and then you have to go right. So you can't just do this with a loop, because if you did this with a loop, then you would just go left, 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 and then you would have to do some way to like backtrack in your loop and then go down to the right. Now, I'm not saying it's totally impossible. You can do it with stacks and while loops, but recursion does the stacking for you. So, I should say it's either recursive or you make your own stack, right? And so that's kind of the idea. So that's why these things are recursive. Anyway, I'm not really going to mess with this. Okay, semicolon. All right, cool. So we've implemented that. So now we just have to talk about the last method that I haven't really talked about, which is remove. And so let's think about how you would remove from a BST. Right, so how do you remove from a BST? And the answer is, unfortunately, it's complicated, but it's, first you find the node, right? So that's not complicated. But after you find the node, what do you have to do? So here's the problem. Here's the problem with delete, right? When you insert, you're always inserting as a leaf, meaning you're always inserting all the way at the bottom or the top or whatever that means. So basically, you're always inserting at the bottom of this tree structure here. And so because you're always inserting at the bottom, you know for a fact that there's never going to be any children to deal with. But for instance here, so if I wanted to delete like 4, that's easy. I just find this node and I kill it off and I tell 3, I was like, 3, your right child's gone, sorry, right? That's what you do. That's easy. But what about if you're going to try to delete, say, 12, 5, or 3, right? Of course, I pointed literally to the wrong ones every time. 12, 5, or 3, right? What if you wanted to delete those? And the answer is that's a little bit more complicated because you see that now they have children and it's hard to know exactly what to do. Like, how do you navigate this where you want to delete 3, for instance? Do I move 1 up here? Well, you could do that. Do I move 4 up here? But then what if 1 has 2 children? Then you would have 1 having 2 children, right? So like if you just tried, like here's some stuff that doesn't quite work, and I think it's good to go through it because then you'll see why we have to do what we have to do. And it's not that bad, but it's if you wonder like why we have to do what we have to do, this is why. So let's make a node down here called 2, because 2 is a number. So the thing is, if we're going to delete 3, and let me make another copy of this so that I can mutilate it. So I delete 3, right? And then I'm like, well, I like 1 more than that, so I'm going to move 1 up into this spot, right? So 1 comes up into this spot here. And then what do you do with 4, right? And if you say, well, I reinsert 4, well, okay. So then we reinsert 4 and it goes down here, and this actually works. But here's the problem with it. What if 4 had children, right? Then we would have to reinsert not just 4. I guess technically we could do this. We could reinsert 4, and then this would be a different deletion method. You could shift one of the children up and then reinsert the other one, and then just make sure. But the only problem with this is that if 4 has a large subtree, then what we're doing is we're shifting all of those nodes up in height pretty hard, because say like there's like this used to be just height like 3 or 2 or however you count. So I hate to tell you this, but unfortunately in binary search trees they don't always count it like consistently. So sometimes they'll start this off at height equals 0, and sometimes they'll start them off at height equals 1. And it will modify the formulas that you have slightly, but nothing actually changes. It's just it's like, do we count an array from 0 or 1? And you're like, well, that matters in terms of memory management, matters in terms of offsets and stuff like that. But if all of a sudden all arrays just started at 1 instead of 0 and went up to n instead of n-1, it would break 99% of all code in existence, but it's a change that theoretically could be made, right? And so that's the thing here, is that either height equals 0 or height equals 1, and it's a little hard to, and I don't actually want to take an opinion, because I kind of like leaving it up in the air, but I liked, when I'm doing in-person like verbal examples, I like to count it at height equals 1, and for mathematical formulas it's always easier, or often easier, to count this as height equals 0. So I'm going to kind of do both. But anyway, so that's one way you can do it. But you see that, like, if, let's say that 4 got reinserted, but instead of that, like, there's huge subtrees here. Let's try to make a subtree. Here's a subtree, and then here's a subtree, right? And if this has another height, then the point is that we'd be inserting this element 4 all the way at the bottom of this subtree here. I'm just kind of, let's say that this is the subtrees of 2. So it's not great, because what could end up happening is you could end up really increasing the height of your overall tree, because if this already had about the same height, right? Then what you're going to end up having is, like, if this had height h and these have height h, if they're all of equal height, then you've just doubled the height of your tree, right? So that's the problem that this creates, is if you just shift one up and reinsert, this will double the height of your tree potentially. So it could actually do worse than that. Well, no, it could only, I think doubling is like the worst. Probably not, that bad, but could be pretty bad. So that's why we don't do that. Okay? So actually, you know what, maybe, whoa. Why are you rotating? Okay, so the actual answer is that we have to find the successor. Okay? And so the successor node is the node which is the largest, or I should say the smallest node on the right subtree. And so the reason why we find that node, so actually we're going to be doing it with 4 anyway, is because if you think about what a successor is, so if we draw out something that's really complicated, then a successor, so what's the successor to 5? The successor to 5 isn't 12, the successor to 5 is actually 8. And the reason why it's good that this is a successor is because if it's the smallest node, the one thing we know, and this is very important, the one thing we know about the smallest node in a tree is that it can't have a left child, right? So at most, the successor has a right child. So there's 2 cases for delete. So basically, for deletion of a node, you find the node, find the node's successor, and then what you do is you shift up the node's successor value into the node. So you don't actually delete the node's memory, you just shift the value up, and then you delete the successor. And so basically, if the successor, so this is where you get into two cases. So case one is successor node is a leaf, meaning no children, right? In that case, you're fine. You just delete the node, right? And then here we have case two. Successor node has a right child. Ha. And so in that case, what we do is we recursively we call delete on the successor node. Okay, and what that does is it then finds the successor's successor and then moves everything up and then does the same thing until eventually, right? As long as the tree is finite, this will eventually end. So basically, this part here can potentially go on for a long time if you build some kind of stupid example. Basically, it go back to step 2, where step 2, if this is step 1 here, this is step 2 here, this is step 3 here, this is step 4 here, so this will be like 4 case 1, 4 dot A and 4 case B, or something like that. So that's the point here. This is how to do it. And I think because this is a Friday lecture that doesn't even really exist, and because of a lot of other things, we will go over this again, and we will do the deletion next Tuesday. And I think that's it for today. Thanks so many people for coming. I hope this was actually a decent lecture. I hope that you learned something about binary search trees. And we'll talk more about binary search trees for basically a month. So yeah, that's so this is like the most fundamental data structure of the course, in the sense that we basically use this to build AVL trees, splay trees, heaps, all kinds of things. We build tons of stuff out of binary trees. And yep, that's it. All right. I'll leave y'all at this point, and have a good weekend.